Hi everybody, I'm Stefanos Baziotis, and this summer I've been doing research on how to loop vectorization legality analysis for LLVM. Now this talk was originally titled for RV, the Region Vectorizer, but RV is just the first user of the analysis. The analysis itself is quite generic, and we intend to keep it that way. However, the fact that RV is the first user is quite important, because RV is a very powerful vectorizer already. It can vectorize inner and outer loops and up to whole functions. And what is missing to make it a full production-ready vectorizer is a legality analysis pass and a cost modeling infrastructure, and we're working on both of them right now. So before I get started, I want to thank Simon Moll for guiding me through this research, because research as a whole was quite new to me. So the analysis is still in early development, you can follow it on this branch, but possibly it already contains some pieces of novel work. So let's get started with the interface. The interface is very simple. Just give it a loop, you get back loop dependence info, and right now it's nothing more than the maximum vectorization factor that you can use for this loop. Now that's great, it's simple and stuff, but we want to improve it further. So one thing we want to do in the future is we want to cache results. So that is, let's say that you're querying an outer loop. So to analyze an outer loop, you basically have to analyze at least partly inner loops. So then if you query another inner loops, because we don't cache anything, you're going to repeat a lot of work. So one thing we want to do is we want to cache results, and the other thing is we want to provide a fine-grained interface. So like pairs of instructions, or maybe an instruction, like can I vectorize this instruction? Because RV can support such a thing. Before I go into what might be possibly novel in this analysis, I want to mention that I dedicated a lot of time on how to deduce dependence vectors, which is like a combination of distance and direction vectors. But later I found out that a lot of this work was already published in this great paper called Practical Dependence Testing. It's really an amazing paper, so I'm not going to spend any more time talking about it and the contents. The first thing that this might contribute, which is actually very intuitive and probably someone else has thought of that already, but since I haven't seen it, let's explain it very briefly. It's basically that when you're deducing dependence distances, basically dependence vectors, you take an arbitrary decision like, okay, I'm going to find the distance or the vector from the right, from the read to the right. So in one-dimensional case, like it's basically just a number. It's like it's that many iterations ahead. So when that distance is negative, what we mean is we have an anti-dependence, and that's an anti-dependence described in the memory access space. Basically, it tells us that the read happens before the write. Now, what we care about is dependence in the iteration space. So this is like this iteration happens before this iteration. Okay, and so if we don't have an anti-dependence, the dependence vector is basically the same in both spaces. But if we have an anti-dependence, we have to reflect the vector to get the iteration vector, to describe what iteration has to happen before another. And that idea extends to n dimensions, where basically if the vector looks in the previous iteration, we have to reflect it. I know this is hard to understand, as well as the rest of the things that I'm going to mention in that short amount of time. Basically just try to keep the high level info, and we can talk about that at some other point, maybe in the poster. So the other thing is the analysis of n-dimensional loopness. So that's quite recent work. I was thinking about it 3 days before, and it's basically analyzing n-dimensional loopness. The idea is, okay, take all the pairs with the dimension that you're vectorizing and analyze them as 2D in S. And if one of them causes a dependence, then you have a dependence basically that's limited by the dimension value that you vectorize. But if not, basically you vectorize for any factor. Again, really difficult to understand such a short amount of time, but the important thing here is we will be possibly able to analyze n-dimensional loopness with an easy and intuitive proof. And the last thing is the analysis of imperfect loopness. Here we note that it is easy to analyze a perfect loopness, so then we can view the imperfect loopness as a tree, and so every path, or like in the tree the root is the outermost loop, and so every path to a leaf, which is an innermost loop, can be treated as a perfect loopness. And so we take the minimum vectorization factor of all those, and that is basically the minimum vectorization factor of the whole imperfectness. Okay, so for the future we're going to do some cost modeling. I'm going to do analysis for tensorialization, which is basically a generalization of vectorization analysis. Lastly, we're thinking about a loop transformation framework. Now, I know that Michael has already proposed a loop transformation framework, and so I would be very happy to discuss about that. So thank you very much. This is my info. You can call on me anytime. Thank you.
Hi, welcome to my talk, Lowering XLA H-Low using RISE, a functional pattern-based dialect. I'm Martin Lücke, second year PhD student at the University of Edinburgh, and let's have a look at how we represent computations in the functional Rice dialect. So here we have the example of a matrix-matrix multiplication, and to compute the yellow output element of matrix C, we perform a dot product of all the values, the green values in the row of A and all the red values in the column of B. This means to compute the full matrix multiplication, we have to compute the dot product for all rows in A with all the corresponding columns of B. And when we look at the Rice program above, we see that this is exactly how this program is written. So the map pattern, which is highlighted in green, applies a function to all elements of an array. And as a matrix is just an array of rows, this applies a function to all rows of A. So for all rows of A, we do the following. And next, again, we have a map pattern, which is highlighted in red and is applied to B transposed. So we do the following for all columns of B. So in an imperative sense, this means for all rows in A, for all columns of B, we compute what's in this blue box. And in this blue box is the dot product represented in Rice. And this computes our matrix multiplication. And one of the main things you should note here is that the matrix multiplication is actually built out of the dot product by composition. This means when we have an optimization for the dot product, it automatically applies to the matrix multiplication as well. So this lightning talk is about how we lower a representation such as XLA HLO using Rice. So let's say we start with a machine learning model such as MNIST for handwritten number classification in TensorFlow, and we want to compile and execute it on a given hardware. And while doing this, we want to leverage the advantages of the functional pattern-based representation. So the first step in our approach is lowering the TensorFlow model to the XLA HLO MLIR dialect. And here on the left-hand side, you see a shortened version of this MNIST model in this dialect. And here we match for supported operations, for example, matrix multiplications or convolutions. And in this particular example, we find two dots, so matrix multiplications in this case, and replace them with the corresponding Rice operations on the right-hand side, which is exactly the matrix multiplication we've just seen. And in consequence, after these steps, the operations that we are interested in are all represented in the Rice dialect. So in this compilation flow, we now have a way to lower our machine learning model down to Rice, so we have a blue arrow. And the natural next step is lowering the Rice dialect. And for this purpose, we use the existing affine and standard MLIR dialects, which provide, for example, the notion of loops or loading and storing data. And so here on the left-hand side, we see the same matrix multiplication as before, now represented in the actual Rice dialect. And on the right-hand side, we see the same computation in the affine and standard dialects. So we see the three loops and the usual access and computation structures of a textbook matrix-matrix multiplication. And we want to lower the left functional pattern-based representation to the target representation on the right-hand side. So let's shift the target representation to the right for a second, because our approach is a two-step process. And the first step is lowering the functional representation on the left-hand side to an imperative representation in the middle. This means on the left-hand side, we have functional patterns like map and zip and reduce. And on the right, in the middle, they have been lowered to loops, indexing computations, and assignments. And here I colored a pattern, and the code is lowered to in the same color. So for instance, the reduce pattern is highlighted in yellow, and in the middle we see the reduction loop, the reduction for loop, also highlighted in yellow. And the second part of this process is lowering the imperative representation in the middle to the target representation, which is affine and standard. So we start already in the imperative world and perform this lowering by resolving all indexings and finish up by generating all necessary load and store operations. For instance, the blue multiplication depends on two values from matrix A and B, which we have to load before the computation. These are highlighted in green on the right-hand side. And now we can use the existing lowering infrastructure in MLIR to lower to LLVM for execution. So in conclusion, we now have an end-to-end system where the input is a model from TensorFlow, and we compile it by progressively lowering it using the MLIR infrastructure, including the Rice dialect. Okay, so today we have a high-level functional pattern-based representation, Rice and MLIR, and an end-to-end lowering flow from XLA HLO via Rice to LLVM. And we have shown in prior academic work, for example LIFT, that this representation is very beneficial to perform high-level optimizations in a principled way via high-level rewriting. So the next step for us is implementing a composable rewrite system in MLIR based on our current ICFP paper. Okay, thank you very much for listening. All the work you've seen today is open source on GitHub, and I'm very keen to hear comments.
Hello everyone, my name is Tarindu. I'm from University of Monitu and I'm going to talk about the work I did this summer with Google Summer of Code. We look at code features of input code and track how the code features change over time when LLVM applies optimizations. And I'll also show you how we can use these code feature changes to optimize our code much more efficiently. Developers usually have to use predefined set of optimization pipelines to optimize their code. So optimization pipelines are a set of predefined passes which are applied to LLVM in order to optimize the code. So LLVM has standard optimization levels like O1, O2 and O3, and developers manually have to select which level they need for their code. The problem with this is these optimization pipelines are not tailored for any kind of application, but rather they are designed to work for any kind of generic application. These are the code features we look at. We look at things like the basic block counts, numbers of different kinds of instructions like load and store, and loop depths. And there are many more code features we can look at in the literature, but these are the code features we could look at during the summer. Here is one code feature, the basic block count, change over time for one module from CTMark benchmark, and when we apply O3 optimization to it. And each of these lines represent a function from the module, and there are gaps in the middle for each line. That's because like different functions get different passes applied to them, so some of the passes are not applied to some of the functions, so that's why there are gaps. And the x-axis is what we call a hyperpass pipeline, so we had to align these passes using sequence alignment algorithms. So this is what we came up at the end after aligning all the functions. Here's how the code, the rest of the code features and how they change over time. And something interesting here is you can notice some of the passes does not like change any of the code features we are looking at right now. So that's something interesting. Next, we wanted to see if we can cluster these functions into groups using the features we extracted. So we came up with 7 clusters. So each color in this graph represents a cluster of functions, and in the second graph we are making it like a bit more easier to visualize it. We are representing each cluster using just one function, the function with the maximum number of passes. And the motivation behind clustering is if we can predict a cluster early on in the pass pipeline, we can tell LLVM that we do not need to apply some of these passes to this function because it doesn't change that. So we actually came up with a predictive model that could predict the cluster each function belonged to with an 85% accuracy after looking at the code features after only 30 passes. So there are around 300 passes. So now we do not need to apply all 300. We can, after the 30th pass, we can tell LLVM this function belongs to this cluster, and that function does not need some of these passes you are applying. So we can significantly save compile time and resources. As a start of how to use these clusters, we look at LLVM standard optimization levels. So we took a set of functions and we compiled them using O1, O2 and O3 optimization separately, and compared the assembly files and categorize them according to the level of optimization they need. So in this figure, the red each point represent a function, and the red ones only need O2, and the green ones only need O3, and the blue ones only need O1. And when we look at the clusters 3, 4 and 6, we can safely say they only need O2 optimization, and clusters 1, 2 and 5 require a little bit more work. What we can do is we can maybe introduce more clusters, or maybe we can introduce more features, and that's it. So if you have any questions or if you want to help me with your resources, time or ideas, please feel free to contact me, and thank you.
Hello everyone, I'm Steve Scalpone and I'm here to present an update on Flang, the LLVM Fortran compiler. I'm the Director of Engineering of the High Performance Computing team at NVIDIA. My work on Flang is supported by NVIDIA, the NNSA Labs, and the Department of Energy Exascale Computing Project. But Flang is supported by many people, individuals and organizations all working together to make Flang a great project. This talk isn't about the code. Instead, I'm going to highlight the many different activities that we have happening right now. Flang was accepted as an LLVM subproject over a year ago, but it was only last spring that the code made its leap into the monorepo. The whole Flang project was pushed in one fell swoop. ARM led the effort to prepare the code for uploading, along with the LLVM GitHub admins, and it all went very smoothly. The initial code push was over 100K lines, and according to GitHub Insights, 2 of the Flang developers were thrust into the top 100 contributors all-time to LLVM. The code base is still growing. Right now, there's about 160,000 lines of code. Once Flang's code was uploaded into the monorepo, things got a lot more real for everybody. A lot more people were paying attention, and a lot of people wanted to contribute in different ways. One of the projects leading up to the push was refactoring the CMake files, which we needed to get into the monorepo. The CMake files are still evolving to be more like other projects. Yet, those people doing the work have preserved some of the unique characteristics of the Flang project CMake files, such as out-of-tree builds and a desire to treat warnings as errors. The original testing infrastructure for Flang was C-tests, but now it's all been converted to lit, which required many tests to be modified. And to make sure everything keeps building, several build bots have been created, including a build bot for out-of-tree builds. Because Flang is not yet part of the default build, most developers don't check their changes against a Flang build. So the new build bots go a long way to keeping the project green. Like I said, being an LLVM project involves a lot more people and a lot more activity. To keep up, the scale of communications had to improve too. The number of people contributing to this effort, from LLVM admins who set up Fabricator and the mailing lists, to the volunteers who added support for generating web pages and documentation files. And the Flang biweekly meetings continue to grow. The project meeting and a technical meeting alternate every Wednesday. Details about these meetings and their schedules and call-in numbers can be found in the Flang Dev mailing list. There's a number of related projects that kicked off when Flang became part of the monorepo too. I'm going to talk about a few of them. OpenACC and OpenMP are directives that are available in C++ and Fortran. They help take advantage of concurrency on multi-core and GPU-accelerated systems. Flang uses MLIR as its IR, so new MLIR dialects were created for OpenMP and OpenACC. For OpenACC, work is ongoing to implement the semantics, lowering, and code generation to LLVM. For OpenMP, implementation of many of the directives can be described independently of C++ or Fortran. So the OpenMP IR Builder project was started to take advantage of these similarities. It's creating a shared infrastructure for implementing OpenMP for C++ and Fortran. Alias analysis in LLVM is very important for Fortran, especially for loop optimizations. Loops are very important in Fortran applications. In Fortran, by definition, is different from C or C++ because in Fortran, most objects do not alias, which puts a lot of stress on the current alias analysis infrastructure. There's a team that meets regularly to discuss how to scale the alias analysis infrastructure to meet the new demands brought on by Fortran. And that's the news. You can find the source code on GitHub in the monorepo. Information about the meetings and the mailing list can be found on the Flang Dev mailing list in the sync notes that are published for the bi-weekly project meeting, and they're posted every 2 weeks. Please, you're invited to join our roundtable this week and check out our project anytime. Thank you very much.
Hello, my name is Alexander. Today I'm going to give you a quick overview of some work myself and my colleagues did over the past year to provide a CUDA backend to Intel's open source DPC++ SYCL implementation. To give you a quick overview of SYCL, in case you're not familiar with it, it's a single source C++ heterogeneous programming model managed and created by the Kronos group. It allows you to write your device kernels in C++ in line with the rest of your program and select devices for them to be scheduled with and dispatched to at runtime. These kernels can also be run as normal C++ at runtime for debugging, or if you aren't on a heterogeneous system to dispatch them to. I'm going to discuss the whats, but not the hows, of the major tasks of implementing this new CUDA backend for DPC++. This includes the Clang driver modifications we had to make, the PI library used by Intel SYCL runtime for device communication, how we interact with it, and we'll briefly mention performance of the backend at the end too. Note that this isn't everything required in a SYCL implementation or in the creation of the CUDA backend, but it covers the major parts of implementing a new backend for DPC++. The SYCL compilation model requires multiple compilations of the initial source file to isolate device kernels and compile them to different targets, be that SPEAR, SPEAR-V, or NVPTX. We had to add a SYCL PTX compilation path to the driver, which would produce PTX from the LLVM backend, then pass it through NVIDIA tools until we get a fat bin we could link and embed in the final application. The host compilation path is a normal C++ compilation path until the final stage, at which point we embed all device kernels in the final binary. The SYCL runtime connects to devices through the PI library, which in turn uses backend libraries for different platforms. The PI library handles each backend library as a separate platform instance with individual devices attached to them. Scheduling is handled by the SYCL runtime, but all device interactions and dispatch are done within the PI library and its backend components. Backends are loaded at runtime only as required. To do so, the PI library provides a function dispatch table that a backend must fulfill and connect to when loading. The first PI backend implemented was for OpenCL, and the functions in the dispatch table reflect this. We implemented about 95 functions for the dispatch table in the CUDA backend. Some were as simple as one-line CUDA calls to replicate the SYCL behavior required, but others were much more complicated and required notable framework within the backend. The PI library also requires a collection of opaque containers that can be passed in and out of a backend library. Thankfully, the containers should never pass between backends, so each can implement the contents however they need. This was very important for certain points during the CUDA implementation where more details needed to be carried inside these objects than in the OpenCL counterparts. For performance and ease, we implemented all the SYCL built-ins we required for the CUDA backend in libclc and linked against that during compilation. In the end, our performance was pretty good, competing very well in benchmarks with OpenCL backend and the native CUDA benchmarks. There's still further space for optimization work though, and we expect to see further speed up in the future. If you're interested, you can get the repo and build from the source at github.com/intel/llvm. We also provide a getting started guide and some code examples specifically for the CUDA backend. Thank you very much for listening. I hope you found this interesting. If you have any questions, you can reach me at alexander@codeplay.com. Stay safe and have a wonderful day.
Hi, my name is Jonas and I'm a software engineer on the debugging team at Apple. Today, I want to talk about adding support for new scripting languages to LLDB. Scriptability is one of the features that makes LLDB so powerful. Since its inception, it has played a central role in LLDB's design. Similar to how LLVM is a collection of reusable libraries, LLDB is really a debugger library, and a library that comes with a stable C++ interface. This interface is called the Scripting Bridge, or SB API. It exposes everything you might need to implement a debugger. For example, the command line driver is implemented using the SB API, and IDEs such as Xcode and Visual Studio Code use it to talk to LLDB. Python is LLDB's main scripting language. There are two ways to script the debugger. One option is to use LLDB from Python to drive a non-interactive debug session. This allows you to leverage all of LLDB's functionality to write custom, standalone debugging tools. A lot of tooling from binary instrumentation, automated bug triage to reverse engineering is built on top of LLDB's Python API. The alternative is to use Python from within LLDB to process data or even extend its functionality through custom commands and formatters. Both approaches give you full access to the debugger thanks to the powerful SB API. For many years, Python was the one and only supported scripting language, and it has served us very well. So then why am I talking about adding another scripting language? Well, the answer is that LLDB was designed to support more than just one language, and I wanted to put that hypothesis to the test. For my new scripting language, I wanted something small and easy to embed. This made Lua the obvious candidate. And if there's anything I learned from Python, it's that you really want a scripting language that's incompatible between major versions. Adding support for a new scripting language starts by implementing the corresponding script interpreter plugin. This plugin powers commands such as script and command script import. Its main functionality consists of running one or more lines of code and importing modules. LLDB's Lua plugin manages the Lua runtime and acts as the intermediary between it and the rest of LLDB. Implementing just the plugin is not enough. Although we can now run Lua code from within the debugger, we can't yet script LLDB because we don't have access to the Scripting Bridge API. To expose LLDB's C++ API to Python, we use Swig, the simplified wrapper and interface generator. It automatically generates glue code between languages, which is a lot less work than writing the bindings yourself. Swig supports many languages, not just Python. Technically, it would be possible to generate bindings for any of the languages listed here. Although, this requires a bit of configuration, which comes with an extra maintenance burden on the project. Although Swig is not strictly necessary to implement a new scripting language, it made adding Lua support a lot easier. For Lua, we only focused on making the bindings available from within LLDB. This is done by linking against the bindings generated by Swig and registering them with the Lua runtime in the plugin. So unlike Python, you cannot use LLDB from a standalone Lua script. With that, we have access to the SB API, just like when using Python. Lua support in LLDB is more than hypothetical or just a prototype. Everything is upstream and available in the latest release. There are some features that are not yet available from Lua though. Callbacks from LLDB into the scripting runtime are not yet implemented. So none of LLDB's extension points can be implemented in Lua. This means you can't write breakpoint or watchpoint callbacks or define type summaries, etc. in Lua. Neither of those are due to technical limitations. I just haven't gotten around to it yet. Supporting these might be a fun project if you are looking for a new way to contribute to LLDB. In conclusion, adding support for Lua validates that LLDB's design allows for multiple scripting languages. The SB API serves as a strong foundation, and Swig makes it possible to easily generate the language bindings. Thank you.
Hello, my name is Yakubova Elvina and I work at Huawei Advanced Software Technology Lab. And today I'm going to tell you how to add support for a specific subtarget to LLVM in just 5 minutes. This guide is based on my recent hands-on experience of adding high-silicon ARM CPU Kunpeng 920 model, also called as TSV110 support to LLVM. LLVM has a unified format for determining the processor properties required for the compiler, which is called TableGen. For each supported architecture, .td files contain a description in a special formal language. All interactions between the TableGen description and the LLVM backend code is provided by the generated .inc files that contain the C code. We will cover Arch64 architecture, so there is a file generate subtarget info.inc from build folder which contains information about our subtarget. As a result, the .inc file is included in MC target descriptor in LLVM target. Since you've learned about TableGen, let's move further through this step-by-step guide how to add a new subtarget. So, firstly, you need to edit your architecture-specific TableGen file. For us, it was arch64.td. In this file, you should add features supported by your CPU and include the file with your description of a model. Secondly, create scheduling categories. You can define them in the arch-schedule file. Then you associate these categories with actual instructions from the instruction info file. In subtarget-specific file, you should describe your processor features. For doing this, define sched machine model based on information you have about specific CPU. It includes things like issue width, micro buffer size, load latency, and etc. Then you define processor resources which impact scheduling. And finally, you can link processor units and latencies to the scheduling categories which were defined on the previous step. Basically, after this, you are done with minimal module description. If you want to add more details in your module, you need to do instruction refining, which means overriding operations with more interesting processor features. In this case, you have to define a new sched write and attach it to the processor units and latency. And finally, associate list of opcodes to the sched write which you defined on subtarget level with the help of inst.rw. To conclude, that's all. Now you can build and check if everything is working fine. That's where LLVM test suite comes. The test suite contains a flexible infrastructure for building, running, and collecting benchmarks and test metrics. LLVM does not include the test suite by default, it has its own repository. The test suite is divided into several folders, which you can see on the slide. External suites contain support for running tests which can be directly distributed with a test suite, for example, spec benchmarks. CMake and the special lead test format are responsible for building, running, and collecting metrics. We use a few options to run benchmarks only and compile all benchmarks for a specific processor using MCPU option to test how our subtarget performs after tuning the model. The results for each test is displayed as shown on the slide. Test suite contains such metrics as compilation, execution, link time, and code size by sections. Results from different runs can be compared using the script included in the test suite. Another tool we used was LLVM MCA. It is a static performance analysis tool that uses information available in LLVM to generate analysis reports for a specific target processor. Important performance indicators from the reports are instructions per cycle, micro opcodes per cycle, and some other useful views are resource pressure, dispatch statistic, and timeline view, which shows instruction states changes during execution. I believe now you have a general understanding of how to add a new subtarget to LLVM without wasting too much time on it and how to test the results of your work. You can use links from presentation to get more information about each topic. Thank you very much for your attention.